Hello, welcome back to Compressible Flow. I'm Professor Steve Miller. Today, we'll be talking about the ideas of attached versus bluff body shocks, when they're attached to the vehicle and when they're not. And we'll do that through the idea and physics of the theta-beta-Mach number equation, which we developed in the previous class. Then we'll talk and look at particular theta-beta-Mach number solutions. We'll then introduce through a number of slides the shock polar diagram, which is nothing but traces of the theta-beta-Mach number equation on a hodograph plane. Then we'll look at particular hodographs themselves, which of course are ideas and projections of shock polar diagrams. Then we'll briefly introduce reflections, and you'll see for shockwave reflections off solid surfaces or say other shocks themselves, they can be solved through the exact same equations which we already developed in the previous class for oblique shockwaves, but applying some extra little tricks and boundary conditions to handle the solid walls. Let's get started. First, let's look at the idea and consider attached reversed oblique shockwaves. In figure 248 of this slide deck, I've shown pictures of attached and oblique shockwaves. The attached shockwaves are at the top, and the detached oblique shockwaves are at the bottom of the page. In the upper left, you have the typical cone or flat wedge in a supersonic flow, and this is the case we previously analyzed, where we have an attached oblique shock shown as a solid line. The solid vehicle, of course, is the line with hash marks. This particular vehicle is at an angle, and you can see that the oblique shock waves are at different angles with respect to the incoming flow because, of course, the flow is being turned by different angles. You can solve this exact problem with the equations we performed in the previous classes. In the upper right is an example of a model ejected from a sabot into a wind tunnel flow to see the Schlieren. You can see indeed the shock waves are attached to the vehicles and at oblique angles. Indeed, we call these attached oblique shock waves. In the lower left, you see a picture of a detached shock wave. It's a bow shock in particular. In this case, the body is a bluff body, and the shock has detached. And these little dashed lines here represent the sonic condition. Since this is roughly a normal shock wave, which is stationary in front of the vehicle, the flow is indeed subsonic behind that shock wave. It then reaccelerates around the vehicle and becomes supersonic again. What's interesting about this case is that the shock wave is a bow shock and is not attached to the vehicle at all, unlike the oblique shock wave case. In the lower right, you can see a particular Schlieren from the same tunnel of a Mercury-type capsule flying supersonically from right to left, and of course a frame is taken. Here the bow shock is shown as this dark line which resides and is off-standing from the vehicle. Take a few minutes and look at the difference of the physics. Now, we're generally able to handle all these problems with the theory we developed, though there's some assumptions necessary when handling the detached shock waves. This is because, of course, the shock wave here has some sort of inherent radius of curvature in it. It's not planar. Earlier, in our theta-beta-Mach number analysis, we only considered planar shock waves. But you'll see we can also present the equations and tables for the non-planar case, which is, of course, shown in your class handout. So why is one case detached and one not? Well, it depends on solutions of theta-beta-Mach number equations. The planar theta-beta-Mach number equation has a solution or multiple solutions for the case in the upper left, which allows for a single planar shock to attach with a turning angle. That is, the turning angle theta, the turning of the flow in the upper lower part of the figure, indeed has a particular solution. You'll see that theta, the turning angle, is relatively small because of the low angle half cone shape. In the lower part, you can imagine the turning angle is very large. In fact, here it's probably around 90 degrees. And theta 90 degrees, there's no solution for the theta-beta-Mach number equation, and therefore we would view the flow as indeed detaching. Let's try and explore this a little bit more in this class. Here's some more figures to illustrate the concepts. In fact, in the upper left and the upper right figures for a wedge, you can see that I have, in one case, for the same Mach number, supersonic Mach number, an attached shock. In the upper right, I have a detached shock. In one case in the upper right, the turning angle theta, the half angle of the wedge, is greater than theta max for that particular Mach number. That means there's no solution of theta-beta-Mach number equation, and therefore I know, and I'll treat the shock as detached for that gamma 1.4 value, perhaps. On the upper left, I have an attached shock, and you can see theta is less than theta max on the theta-beta-Mach number equations and charts, and therefore it has particular solution or solutions, and I can get an attached shock. This can also be translated to the wall problem, where a turn happens in a wall, which is shown in the lower left and lower right parts of figure 2, 4, 9, respectively. You see in the lower left, I have supersonic flow, and I have the same turning angle theta as the upper left case. But you can see now a shock attaches because I have a solution of the theta-beta-Mach number equation. In the lower right, I increase theta over theta max, and I retain the same Mach number and the same gamma, and my shock in fact detaches. Now, if you compare the upper right and lower right, and the upper left and lower left figures, respectively, and draw a line of symmetry through them, you can see they are actually the exact same flow according to the viscid equations of motion in 2 dimensions. Here, we would actually find the same relative solutions if we were using a CFD solver. That's very interesting, because of course we made these particular assumptions. In reality, there's turbulent boundary layers in the lower cases because of the effect of viscosity and the stress tensor within the Navier-Stokes equations. Let's make some particular notes from these diagrams, which can be rules of thumb that you can remember to understand the physics. Here, if theta equals 0, that is, the turning angle of the flow is 0, and then beta must be 90 degrees or pi over 2. That means indeed a normal shock is happening if a shock is occurring in the theta-beta-Mach number equation. Remember, theta is 0 is at 0 turning angle, so that's just like a normal shock wave. Now if beta equals mu, that is the Mach wave angle, then of course a Mach wave will have formed. So beta equals mu will correspond to Mach waves in the equations of motion which we developed for this particular solution. Now, if theta is a constant, we hold theta constant and we decrease m1 from very, very high values to very, very, very small values, then of course the wave angle beta will increase. And you can see that by holding theta constant and seeing decreasing Mach number solutions on the theta-beta-Mach number chart. Try that out for yourself. Take a second and bring it out and look at it. Next, you can see that for very, very low Mach numbers, even with well-behaved angles, the shock waves indeed detach. And that's very much like very, very, very low supersonic flow. That is where like a transonic condition would happen with a global Mach number just greater than 1. Finally, you can see, and as we previously mentioned and shown in the following previous 2 charts on 695 and 696, then indeed there is no solution whatsoever for the theta-beta-Mach number equation for theta greater than theta max. These are some important points that you'll need to remember to understand if we have a detached or attached shock wave to a surface or vehicle. In fact, remember, in the wall flow and a bounded flow, and like in the lower right, you can see even though we have a detached shock, it is connected at the leading part of the wall. This is just like the bow shock problem. So don't think the shock is really detached from the wall. It's just detached from the leading edge. This is a subtle point, but important to remember for the physics of the class. Now let's return and do some more analysis of the theta-beta-Mach number equation and relation. You'll see that indeed we have not found closed form solution for the other variables, but we'll try and find some closed form solutions for the other variables now. We showed that the calculations indeed reflect the nonlinear behavior of the equations and often have Mach squared terms. So this is a very difficult equation to work with to find closed form solutions. This is especially true in a nonlinear algebraic equation of the theta-beta-Mach number relation. Let's recall our theta-beta-Mach number equation now in 516, which we developed in the previous class. You'll see that the tangent of theta, that's the turning angle of the flow, goes as 2 times the cotangent of beta, all of m1 squared sine 1 squared beta minus 1, all over m1 squared gamma plus cosine 2 beta plus 2. Remember, m1 is the incoming Mach number before the shock, and beta is the angle of shock relative to the incoming flow direction. The incoming flow direction, remember, is the direction of the flow right before the shock face in front of the shock. Now, theta will be a term which we want to seek. For example, if we know the incoming Mach number and wave angle, how can we find the particular deflection angle and or the upstream Mach number? So usually we can measure or observe these, and we can find the third quantity. Now, if we want to find beta, of course, it's not that hard, because we can find numerical solutions today or find it graphically with the chart, which is of course also created with numerical solutions because we don't have closed form solution. Maybe. There is one method, at least one that we know of, to find the wave angle beta. Let's do this now, and you'll find this is an interesting approach to analyze this type of equation. Write out the theta-beta-Mach number equation as a cubic equation, and then find its particular roots. Let's do this now. We'll take 516 on this slide deck and write it out as a summation of cubic roots involving sine. We'll find sine 6 beta minus the factor here, sine 4 beta, plus this factor, sine squared beta factor out, minus cosine squared theta over m4 equals 0. We can rewrite this now after this work in another form, in terms of tangent cubed, tangent squared, and tangent, using, of course, identity. We can now see we have a way to solve this equation. In fact, you'll see in this particular equation there's some particular important facts. It is a cubic equation, and looking at its coefficients for analysis, we find that it indeed has 3 unequal roots. Unequal roots, 3 of them, as solution for the attached shock problem for particular values of theta and Mach number. You'll note that one of the 3 roots, if you do the analysis, is indeed negative, and that would mean that we have a negative angle into the wall, which is not physically possible to our knowledge, and that's not useful. It does indeed have 2 positive real roots, which correspond, respectively, to the weak and strong shocks within the theta-beta-Mach number charts and equation which we looked at in the previous class. That's amazing, and it's very useful. And so we have indeed analytical equations for beta in terms of 3 particular roots. You can imagine indeed, though, that it is possible for one of the waves to go into the wall, mathematically at least. But of course there's a wall there, so it won't be happening physically. Let's look at these roots now. We'll find, if we go through the root finding, tangent beta of m squared minus 1 plus 2 lambda cosine, and I'll introduce lambda in a second, of 4 pi delta, and I'll define delta in a second, plus cosine negative 1 chi over 3, and I'll define chi, all over 3 plus 1 plus gamma minus 1 over 2 m squared tan theta. Now if we set delta 0, we'll actually find the strong shock solution, wave angle for beta. If we set delta equals 1, we'll find a weak shock solution. Here, lambda and chi are only functions of Mach number, incoming Mach number, the turning angle theta, and of course, gamma. You'll see that these represent the particular solutions of the useful roots of the strong and weak shock. This is also viewed and called the alternative form of the theta-beta-Mach number relation. And you can see it does indeed give us explicit calculations, closed form, for beta given one particular theta and Mach number for the strong and weak solutions. You can also try and develop a particular solution for m, but that might be rather difficult. Now let's turn our attention to an alternative way of examining these equations through the shock polar diagrams. The shock polar diagrams are one particular traditional approach in the field and are not used typically today, but we're going to return and look at them because they indeed have an excellent way of examining the oblique shock wave family of solutions. The shock polar is one particular graphical representation of the solutions, which we'll look at in a few minutes. Let's return to our physical plane, and we'll transform or project this physical plane into the hodograph plane, which I'll define in a second. Once again, we have an attached oblique shock with a turning angle theta. Before and after the shock, we can decompose the velocity components as a sub x and a sub y for the x and y directions respectively across the shock. Let's take these coordinates and define the hodograph now. We can use the particular components of u, the velocity in x and y directions in axes, where u, x, and y are the velocity components, and we'll plot the hodograph. So we have a velocity component in front of the shock and after the shock in terms of its components. The hodograph is a graph of the velocity components, where on the x-axis we have vx, and on the y-axis we have vy after the shock. So x-axis is vx1, that is u sub x, or v sub x, and after the shock we have v sub y2. You can see, of course, v sub y1 is 0 before the shock, so it doesn't have much meaning. Now, we will plot the particular vector v sub 2, that's the velocity vector, of course, after the shock, with its components vx2 and vy2, as shown here. So remember, the axes are the velocity in the x direction before the shock, the velocity in the y direction, essentially after the shock, and the vectors vx2, vy2, which is shown on the right in state 2. Okay, that represents this solution. Now you can imagine we can vary some of the values, like vx2 or vy2, relative to the theta-beta-Mach number equation and velocity vector solution before and after the shock. And this will trace a family of particular solutions. Let's do that now. From the origin to point A will be the velocity ahead of the shock, as in figure 252. Here's the origin, and here's A, velocity ahead of the shock. Line OB will be the velocity behind the shock, which is that velocity vector from O to B, right here. Next, point A is one particular state representation of the flow field ahead of the shock. It'll always be on the x-axis. Point B is one particular state representation of the flow field behind the shock. So you can see points B and C are two velocities after the shock, which depends on the particular angle, the turning angle. Now, we'll consider a new hodograph where theta c is the increase to a higher value, and of course u2 will decrease behind the shock because we've increased the turning angle. You can see this from the theta-beta-Mach number charts or physically. So here we have two particular representations. One is dependent on theta b, which is the turning angle for this family of solutions from the origin to B. And the second solution is dependent on a different turning angle, theta sub c. You can see they both have different velocities v2. You can also note that for one particular theta b or theta c, for a valid solution with theta-beta-Mach number equation, will trace a beautiful shock polar diagram for one particular solution. You'll also see that the solution is indeed multi-valued. For example, we'll have one solution here and here. So there's two solutions for each theta b or theta c, just like the theta-beta-Mach number equation. Now let's go through and do the hard work for you and choose different Mach numbers, which are representative of the velocities. Here's the shock polar diagram from Shapiro's book, but instead of velocities on the axis, he has shown, indeed, values of Mach number and normalized the curves. For increasing Mach number 1.2 all the way to maybe 10 at some increment shown here, he's traced out a family of shock polar diagram curves. So this is the hodograph of the shock polars. Now, it used to be that there's tables of these particular books for different gammas where people can look up the particular shock properties and understand them physically. For example, for any small turning angle, like say 10 degrees, there's a whole family of solutions. For Mach numbers greater and do not align along the line of 10 degrees, there indeed is no solution, and that would be a detached shock. The dashed line here, of course, is that sonic condition Mach number, where indeed no solution will exist at Mach 1. It's a point. Now this shock polar diagram shows that there's a locus of all possible M2 sup star for the given values of M1 star. We'll also limit that as M infinity goes to infinity, M sup star will go to 2.45 for gamma 1.4, and you can see this indeed in this chart. There's indeed a wide range of Mach numbers, in fact an infinite number of Mach numbers that fit inside the particular diagram. You'll also notice that the circle of M sup star equals 1 will encompass all subsonic values, Let's briefly look at a few other types of shock polar diagrams from Shapiro's book. On the upper right, you see one particular figure. They've projected the shock plane across the whole y-axis domain. Once again, they have u over c sup star and v over c sup star as a different normalization. And they can use, indeed, trigonometry, like in shown in the upper left, to show certain properties of the shocks before and after the shock. This is how people generally understood, through geometry alone, the properties of the theta-beta-Mach number equation. You can construct these types of shock polar diagrams like Shapiro did through this particular notation. One interesting thing which you'll find is that for a particular solution, if you draw a line from A to B for a given theta, so B, of course, is that velocity vector after the shock. A is the vector before the shock. And you draw a line over the weak solutions, and you make that line perpendicular with a line projected from the origin. That angle indeed will be the angle beta of the shock. So some students very much prefer to view and understand shock polar diagrams graphically and geometrically, like in these particular cases. This is much easier for some people than perhaps just working with the equations or working with the physical solutions. I suppose it's just the way different people think. You can also see that indeed from the origin to point C, which is a line which is tangent with the single shock polar for one Mach number, that angle indeed is theta-max, which can be seen from the family of solutions like here. Let's now make some important points for these particular diagrams. For a particular turning angle theta, the points y and x, that is, on these curves, will represent the weak and strong solutions. For example, x and y are weak, y is weak, and x is strong solutions on the particular shock polar. The line 07 on my previous diagram represents theta max, as I noted. Here's theta max. Points x and a will represent the flow with no particular deflections. That means there'll be a particular normal shock. That is, A will be a Mach wave and X will be a normal shock wave. So out here in the weak part of the solution, A with no turning angle will be a normal Mach wave solution, and X will be the normal shock solution. And you can see that on the y-axis of the theta-beta-Mach number charts. The line from A to Y will be an angle beta, where beta is the so-called triangle, which gives us, and I just explained previously, of the turning angle of the flow. So the angle from 0 to Z with 0A is, of course, the turning angle of the flow right here. Great. Now, shock polars for different Mach numbers form a particular family of curves. So, for example, the M1 sup star equals 2.45 becomes the circle. That's the so-called sonic circle. Now we have one last important point about the so-called family of shocks in the shock polar diagram. We can plot out these plots for shock polars by a closed form analytic solution, for example, with u sub y, which is the velocity in the cross-stream direction after the planar oblique shock. That's the induced velocity in the cross-stream direction after the shock wave. And this is I show without development in equation 522 of this slide deck. We'll see that u sub y over c sup star squared goes as m1 sup star minus ux c sup star squared times u sub x c sup star m1 star minus 1 all over 2 gamma plus 1 m1 sup star squared minus ux over c star m1 star plus 1. You can develop this equation yourself by simply using our planar shock equations and the theta-beta-Mach number equation and writing an explicit solution for u sub y and normalizing it over c sub star and squaring it as a function at m1. You can try that for yourself to try and recover equation 522. It makes an excellent problem, so you can see if you understand the physics and mathematics accurately. If we plot 522, you'll see we find figures like 258 of the slide deck, which I call the shock polars for different Mach numbers. For example, in 522, I would choose a particular M1 and hold it constant, for example, at 2. I can then trace out u sub y for those particular solutions by varying, of course, theta, the turning angle, and I'll get these beautiful concentric little curves. You can see one beautiful thing happens is that as I let m1 go to infinity, there is a bounded solution in this particular case for particular turning angles and Mach number. And that is bounded between 0.41 and 2.45 on the shock polar diagrams for gamma 1.4 for uy over c sub star squared. A beautiful equation. And it forms, of course, the perfect circle. Let's now change our attention to the idea of what happens to a shock wave when it hits a wall. Certainly shock waves are formed and we understand their formulation, but if they're in a closed duct or if they hit the ground from an aircraft flying over, what happens to them? And that depends on the shape of the surface itself. For now, we'll consider what happens when a shock wave bounces off a simple flat surface. And this is one particular Schlieren to illustrate the physics of this particular concept. Here in figure 259, I show a Schlieren image of a shock wave reflecting from a wall. The wall is the black part of the figure that's solid, and here's the edge of the wall right here where my cursor's moving. Now, the flow is this light gray color. Up here in the upper left, I have supersonic flow. I have supersonic flow here where my cursor's moving. And I have supersonic flow to the right. The flow moves from left to right. A shock wave, which is left running, is if I look downstream, I can say that it's moving left from my left hand. I can look to the left, and that's the direction it's going. It's to the left with respect to the flow. It hits the wall, and it reflects as a right-running shock waves. Now, it's very interesting because if there's a particular turning angle at the wall, that is, the wall changes its direction with respect to the flow, from respect to region 2 and or 1, you can see then that the shock reflection might change. It might not reflect from a shock. So right now, we'll just say that the turning angle of the wall for the reflected shock is 0 and analyze this case. We'll look at the other cases with non-zero wall turning angle in the next classes. So this is what happens physically in the Schlieren. Typically, you'll have supersonic flow through the whole regime, not always, but typically, and you'll have a left and right running or right and left running waves respectively with a typical shock reflection. Of course, you already know that the Mach number is decreasing after every shock because we have supersonic flow in front of each shock. Let's try and draw this out and understand the physics and describe some notation, and we'll analyze the problem. Now you'll see in this particular diagram, the flow is bounded by a lower wall and indeed an upper wall. In this case, the incident shock, which is left running, moves along and impinges on the upper wall. Like in the Schlieren image, we know that in this case, the shock indeed must reflect. And indeed, there's a solution of theta-beta-Mach number equation for particular reflected shock. Why is that? Because it appears that the flow turning angle is not 0 between 1 and 3. But indeed, the incident shock has been turned into itself by an angle theta from point A. And so whole fluid is moving in the upper direction on this particular figure in the left running direction by an angle theta. Notice the streamline coming in here in front of the incident shock, and it's turned to the left by an angle theta. Now, of course, the flow cannot go into the wall, and so the flow must be turned by an opposite angle theta for the straight wall case so that the flow in 3 is parallel to the wall, which is not true from 2. So the reflected shock forms, and the Mach number in 3 will indeed be dependent on the flow turning angle and the incoming Mach number M2, which is the Mach number after the incident shock. A new shock wave will form and it'll be right running, and we call this the right running reflected shock wave right here. Indeed, this shock wave will have a third Mach number after it, m sub 3, which is basically m sub 2 in the theta-beta-Mach number equation. So once again, we can solve these equations by applying the theta-beta-Mach number equation and oblique shock wave equation solution approach twice. The first time we'll go from 1 to 2, and the second time we apply it, we'll go from 2 to 3. We also call that the second shock wave angle might be capital phi. So let's summarize what we see. A flow moves from left to right. There's a turning angle on the lower wall, which creates an incident shock. The incident shock wave reflects off the wall. The flow is deflected first to the left at angle theta, and then to the right at an angle negative theta, if you will. There'll be two particular wave angles relative to the walls and initial flow condition. The first one's beta 1, and the second one's beta 2. You'll notice that beta 2 is an angle which is respect to the initial flow direction before the reflected wave, which is of course theta. So look at how we draw theta and beta 2 for the reflected shock wave. Indeed, there'll be another new angle we reduce called capital phi, which is respective to, of course, the original wall direction to the reflected wave. Let's make some notes, important notes about what we have seen so far in this particular problem. We know that reflected shock waves must turn the flow again by an angle theta, as we shown in our diagram and on our Schlieren. 2. All flow conditions will only be functions of each individual flow turning angle and incoming Mach number. At point B in the particular figure, the flow must be deflected again by angle theta to keep the flow parallel to the wall and enforce continuity, which is right here. What will happen if the shock impinges on a corner? For example, if B is not a straight wall, it could be a wall which maybe moves to the left as it goes downstream or moves to the right as it goes downstream. Multiple things can happen. Perhaps the shock wave is canceled out and the flow continues on without any shock. It could also be that a different kind of shock wave will occur because the turning angle will be different relative to the straight wall case. So that angle theta will be dependent on the flow direction parallel to the wall after the reflected shock. We also know that M2 must be less than M1, and also M3 must be less than M2. It's also very much possible to have strong shocks where we have subsonic flow after the particular shock, which terminates the supersonic flow, and we have no subsonic shocks afterwards. We also know that indeed beta 2 must not be equal to beta 1, unless there's a very particular wall angle. For example, here's beta 1, and here's beta 2. They cannot be equal because, of course, for the two parallel wall assumption, that the Mach numbers are changing with respective equal turning angles of the incident and reflected shock. So therefore, phi, capital Phi in the previous diagram and phi in my notes here, is the angle of the reflected shock which must make with the upper wall. And you indeed can find this with all the equations in physics we now understand. You should try some marching problems like we do in the homework to fully understand the concept, or work through the equations in this diagram yourself. Try and remember the physics which only comes out of the mathematics and our basic observations. Today, we looked at the famous attached versus bluff body shock waves through diagrams and Schlieren. We just then interpreted them as being no solution or a particular solution of the theta-beta-Mach number equations. Therefore, you have a way to estimate if the shock is detached or not for planar type oblique shock waves and flows. You'd have to use different forms of the theta-beta-Mach number equation for, say, a conic shock. And we show these diagrams in our class notes and handouts. We then discuss the historical context and physical significance of the geometric derivation of oblique shock wave theory through the famous hodographs or shock polar diagrams. We then talked about the physics of the reflected shock wave on a straight wall. And you can see for this particular case, indeed, there's absolutely no difference between our previous theory and the present theory for reflected shocks on hard walls. However, know that different things happen if the wall deflection angle is non-zero. Remember, the wall must be turning, that is, if it's a straight wall, a reflected shock at the same angle as the incident shock deflection angle. This is important to remember when you're solving problems. Thank you very much for your time today. I'm Professor Steve Miller.